grey molecule. We might as well make a start. I'm not getting any younger here. So, I'm not going to bother introducing myself because you all know who I am.
You really think that David Paterson? Take a step to this side.
Right, so tonight we're going to talk about something that's quite close to my heart in many ways, the art of navigation and its connection to astronomy. Now,
lights
yes. There's no really fluorescent slides here, but probably easier to read if you've got
Who's the popcorn man?
So, I think most of you know me. I've been interested in astronomy since I was at school many years ago, and I've also been interested for a long time in the history of astronomy, or history of science in general, but in particular astronomy, and how it's evolved from early beginnings, like our ancestors who watched the movements of the stars and the sun and the moon and devised calendar systems, built huge monuments and knew when to plant their crops and various things and mark the passage of the seasons, and how that's evolved through to modern astronomy and the amazing discoveries we've made about a place in the universe. And then, supplemental to that, about 12 years ago I discovered a love of sailing. Not messing about on yachts, although I do a bit of messing about on yachts nowadays, but I jumped in with both feet to the world of tall ship sailing and crossing oceans. And I chose as my first port of call, or my first vessel, the rather wonderful bark Europa, a Dutch three-masted bark, and it's a sail training vessel, which means they train their crew in all sorts of things like traditional seamanship skills, like rope work, sail making, carpentry, and of course celestial navigation. So it was natural for me to take an interest in that because of its astronomical connections, and then start to think about the origins of celestial navigation as a subset of astronomy, if you like. Now, as with most of these things, the origins of celestial navigation, or navigation in general, are lost in the mists of time. But we know that humans have been exploring and travelling and trading for a very long time. This is a Bronze Age logboat which was discovered actually in the Tay, just upriver from here, at a place called Carpow, which is just past Newborough. And you can see it's a substantial vessel, if you like. It's about 9 metres long. It would have been certainly capable of carrying multiple people or cargo, trading between communities along the river. And rivers and waterways and the coasts were important trade routes back in Neolithic and Bronze Age times, because they very often were a lot easier to navigate, a lot easier to pass through than trying to go overland through what would have been at that time fairly dense woodland and forest. It's not suitable for going out to sea though. It's a fairly basic boat. It has got no keel for stability. There's no sign of any way to attach outriggers, which would make it more stable, and there's no mast fittings for making it sailable. So it's basically for paddling up and down the river. But certainly the origins of long distance travel up and down the Tay, as you can imagine. To look for the origins of celestial navigation using the stars, we go back about 4,000 to 5,000 years to the civilizations that grew up in the Eastern Mediterranean and the Persian Gulf. And one of the most successful were the Minoans. These were a race based in Crete, and they survived from 3,500 BC to around 1450 BC. And they traded widely through the Eastern Mediterranean, and as you can see, they also headed over to Spain west to trade for copper and tin, which is the makings of bronze. And a lot of these voyages would have been a few days, certainly several days on some of the longer ones, and would have been out of sight of land for a good part of the voyage. If you're just navigating around a coast, it's easy enough to keep in sight of land and know where you're going. But once you get out to sea, you need to have some sort of reliable navigation system. Now, we don't really know a huge amount about what they used. We certainly know from writings and a few artefacts at that time that they did use the stars and the sun, and they used the sun because it would rise to the east, and at noon it would be at its highest point and due south, so that's a good marker. And at night, the polar constellations around the celestial pole would give a good guide as to where north was. So they used these as the basis of their navigation system. Their boats were certainly a bit better than the log canoe that we saw. It's a fairly decent sized boat, capable of navigating around the Mediterranean, and would have required a reasonable crew, and they certainly needed to be able to navigate successfully in something like this. Now, as I said, we know how to find Polaris. We're all astronomers, so we should recognise the constellations Ursa Major and Ursa Minor, which I think is one of the first things that almost everybody learns in astronomy. You find the plough or dipper or saucepan, you find the pointer stars and draw a line north from the pointer stars, and you come to Polaris, which is the tail of the Little Bear. And of course, from a time-lapse image you can see, this is a rather nice one, that the pole star is in fact very close to the celestial North Pole, but not quite on it. But it's good enough, as I say, for government work, good enough for navigation. So knowing where the pole star is, you can navigate. At least you know where north is and you know which direction you're going. However, back in the time of the Minoans, Polaris was not the pole star. The Earth's axis moves around like a spinning top in what's known as precession, and we're currently here at plus 2000. But if you go back to the time of the Minoans, this star, Thuban in Draconis, or Draco, was the pole star. And over the millennia, the pole has moved, and in 2000 years' time, it will be Gamma Cephei, or Eri as it's known. So we'll have to redraw our map of the heavens when that happens. Now, for actual navigation at sea, there is a very useful measurement you can make. If you know where the celestial pole is, whatever the pole star is, it's useful to be able to measure the height of that celestial pole above the horizon. Again, we don't have any artifacts of measuring instruments, but it's very easy to estimate angles in the sky just using your hand at arm's length. Varying, of course, depending on how long your arm is and how big your hand is, but in general it's fairly accurate. So they would have been able to measure the height of the pole above the horizon using this sort of method. And it turns out that the angle of the pole, the celestial pole above the horizon, is equivalent to your latitude, which is a very useful piece of information. So if you ever get a chance to get a nice clear sea level horizon, you can try measuring where Polaris is, and if you're doing it from Dundee, it should come out about 56 degrees above the horizon. I've lost my place. Oh yes, knowing that the angle of the pole star changes linearly with your latitude or linearly with distance, and the fact that new stars appeared in the south as you moved further south, led the early navigators and sailors, and of course the astronomers, astrologers, priests, who were kind of the same thing anyway, to realise that the Earth wasn't flat, that it was round or spherical. And it's been pretty much known to most people for thousands of years that the Earth is round, and the myth of sailors in the time of Columbus or Magellan thinking they were going to fall off the edge of the Earth was actually a fantasy propagated in the 18th and 19th century. It's a bit like some of the nonsense we hear about nowadays. So as I said, the Minoans flourished for about 2,000 years, but in 1450 BC they disappeared. We're not 100% sure of the cause, but it's possible that the explosion of the island known as Thera, which is now known as Santorini, could have been the cause, and it may have given rise to the legend of Atlantis. It blew up with incredible force, and it would have caused huge tidal waves which would have swamped the coastal communities. It probably produced a huge ash cloud that would have blanketed farmland. And it's likely that the Minoans either were devastated completely or they were made much more vulnerable to invasion and conquering, possibly by the Mycenaeans, who were quite a warlike society at that time. However, the Minoans were fairly quickly replaced by another few groups of traders, the Phoenicians and Greeks. The Phoenicians are legendary seamen, sailed long ways, as well as the Mediterranean, Spain. They explored up into the Black Sea and even round as far as the south of Britain for tin. So there was plenty of tin mines at that time in Britain. There are also reports that the Phoenicians sailed down the west coast of Africa as far as Gabon. And there is a report, although it's of dubious veracity, as they say, that the Pharaoh Necho II in 600 BC commissioned a Phoenician crew to sail from the Persian Gulf end of Egypt down and around Africa and back into the Mediterranean, taking 2 to 3 years to make the voyage. And one piece of evidence that supports this is the report that nobody believed, that when they were sailing further south, that as they sailed west, the sun was on their right, which was completely unheard of. Again, the Phoenicians and Greeks used stars and sun in the same way as the Minoans did. And the constellation of Ursa Minor in Greek at that time was called Phoeniki, meaning it was of particular importance to the Phoenicians. And we also have evidence from Homer's Odyssey, where Calypso says to Odysseus to keep the bear on his left and watch the Pleiades and Orion as he sails east from her island. So we know that Polaris, a quick picture of a Phoenician reconstruction. Again, a bit bigger than the Minoan one, and a nice seaworthy boat, plenty of cargo carrying capacity. So you can imagine this sailing up to the south of Britain, trading for tin, or all over the Mediterranean. So, knowing that the latitude changes with the height of the pole star changes with latitude, you have a very simple method of navigation, which was in use at this time and for quite a while after, in that if you know the latitude of the place you want to go, your destination, what you can do is you can sail north or south until you reach that latitude, and then change direction, sail east or west, and it should bring you to that location. So you need a way to accurately measure your latitude, so you can stay on that line. And one of the first navigational instruments that we know of is called the kamal. And in essence, it's a rectangular piece of wood with a hole in the middle and a string with knots in it. And each knot represents a particular destination, or the latitude of that destination. And in use, the navigator would hold the knot that he wanted to sail to in his teeth, stretch out the string, and the board would then be the exact height of the pole star above the horizon. And in this case, the knots are not, for specific destinations, they are now evenly spaced. In the later versions of the Kamal, it has evolved from a simple navigation tool to an astronomical measuring instrument. And the Kamal was certainly in use by the turn of the millennium into the 1st century AD, and very probably used by the Phoenicians and Greeks as well. About the same time as we moved into the 1st millennium AD, there was another group of navigators exploring the world, and in a totally different way. And the Vikings, I think, have had slightly worse press than they deserve. Certainly they were prone to a bit of pillage and plunder, but at the same time they did some incredible voyaging. They built up colonies all over northwest Europe. They sailed down into the Mediterranean, the Black Sea, and there are reports of Viking remnants or finds further east than this as well. They also reached America long before Columbus ever did. They had their own unique instruments, which were unlike any from other cultures. One of these is the Viking Sundial. This is a relic which was found in East Greenland a few years ago, and based on a reconstruction, it's fairly likely that it was used in two ways. One, to find north, depending on the angle of the sun, and also the curved line, which is seen on it, could be used to sail on a particular latitude using the sun's shadow cast on that line. And the relic that we have here has been calculated to match a sailing of a latitude of 61 degrees, which comes from just north of Bergen, past the tip of the Shetlands, within sight of the Faroes, and then on to East Greenland. So a very simple and interesting tool, and completely independently developed. The other legendary Viking tool, which was mentioned in a few writings, in a few of their odes and poems, but not found until a few years ago, was the Sunstone. And it turns out this is a crystal of Icelandic Spar. Even on a cloudy day, the polarised light from the sun shining through the crystal will create two bright spots of light. And by rotating the crystal, and I'm not exactly sure how because I haven't managed to get hold of anything to test it with, but I believe that when the two spots are as close in brightness to each other as you can get them, the angle of the crystal will tell you exactly where the sun is in the sky. So even if it's completely overcast, raining, you can still figure out where the sun is. And that's an important tool for navigation, since you want to know which direction south is at the best of times. Another favourite navigational instrument is the compass, of course, developed in China from about the 1st century AD. It didn't arrive in the West for about 1,000 years later. The Chinese used a little fish floating in water shape, and they had it pointing south instead of north, but in essence it's the same principle as the magnetic compasses that we use today. The early mariners' compasses from sort of 13th, 14th century are just as usable today as they ever were. And the astronomical correction, of course, is that they don't rely on anything in the heavens, but they do rely on something deep within the Earth, which is the magnetic field. It's something that we are only now beginning to fully understand the mechanisms behind, and it's generated in the outer part of the core, which is the molten part, and the magnetic dynamo in there creates a strong magnetic field. Exactly why we have this leads to questions about the formation of the solar system. How did it come to be? And Earth is lucky enough that it was formed from a collection of pieces of debris which were rocky but metal rich, so there was enough iron to sink down and form the core. It was also lucky enough to be large enough that it didn't cool down quickly. Mars is made of almost exactly the same material as Earth, but being about half the size, it cooled down very quickly and it now no longer has a magnetic field. As we move forward, looking at instruments, by the time we get into the 1000 AD period and onwards, we have things like this Astronomical Astrolabe, which is a beautiful instrument capable of taking lots of different measurements of things in the sky. It's far too complex to be used for navigating at sea because of it can measure many different things and tell you dates, times, angles and so on, but very unwieldy for use at sea. So over the years a simpler version was developed called the Mariner's Astrolabe, which has only one function in life, which is to measure the altitude of some object above the horizon. And you might recognise the Mariner's Astrolabe as being the logo of Dundee Astronomical Society. So I'm afraid to say we're using a mariner's tool rather than an astronomical observing instrument as a logo, but it's a lot easier to put in a logo than the complexity of something like the Astronomical Astrolabe, beautiful though it is. So in use, the Astrolabe, basically hang it and try and keep it level, sight through the sights on the sun or the pole star or whatever you want to measure, and then you can read the angle off directly on the scale. Not easy to use at sea on a ship that might be rocking and rolling, but it was used quite successfully for centuries as the prime navigation instrument. Another common instrument about the same time as the astrolabe is the quadrant, and this again is used simply by sighting through a pair of sights, and then when you have a good sight and everything seems to be stable, clamp the plumb bob to the scale and read off the angle, which on a ship that's rocking and rolling and with a bit of wind blowing the string about, I can imagine was not an easy task. But again, these were used successfully for many years to navigate all over the world. By the time we get to the 14th century, there's another interesting instrument which you can experiment with. This is the cross staff. Simply consists of a linear scale, well, a gradiated scale, it's not linear in fact, and a cross piece called a transom, which can slide up and down. The full cross staff has a number of different sizes of transom, and you choose the appropriate one that you want to use. And in use, you simply sight so that one end of the transom points at the object you want, the other one at the horizon. This should actually be more level and tilted up a bit. And then the angle between the two can be read off on the scale. So a very simple and easy to use instrument. As we've seen, the latitude can be found by measuring the height of the pole star at night, but measuring your latitude by day isn't easy. And it took developments in the mathematics of navigation until we had things like Abraham Zacuto's tables from 1473, which for every day of the year would tell you that for a noon sun sight, which the sun is at its highest, you could work out from the tables exactly which latitude you were on. So this is the forerunner, if you like, of the celestial navigation as we know it today. One problem of things like the astrolabe and cross staff is that the user has to look directly at the sun to use them, which is not easy and also not good for your eyes. So in the late 1500s, Captain John Davis developed the Backstaff, or Davis Quadrant. This uses a shadow vane, so the sunlight hits the shadow vane and creates a shadow on this horizon vane, and then sighting the horizon through here, the sum of the two angles gives you the angle between the horizon and the sun. So you're no longer looking at the sun, and it makes it a bit easier to get an accurate reading. So in the age of discovery, which you might call the time when great voyages were being made all over the world, navigators' equipment was fairly crude. You had compass, some sort of way of measuring angles, tables, and maps of dubious accuracy, shall we say, in some cases. But yes, generally the maps improved quite rapidly as explorers started getting detailed pictures of where they were visiting. So at that time, it was not an easy job being a navigator. However, we've only really looked at one half of the problem of knowing where you are on the planet, because we've talked about latitude, which is your distance north or south of the equator. The other thing you need to know to figure out where you are is your longitude, which would be east or west of Greenwich. Well, it's east and that's west. And this is essentially a problem of measuring time, because as the Earth rotates and objects in the sky move relative to us, every degree east or west of Greenwich is equivalent to 4 minutes of time. So 15 degrees is an hour. If you can work out when local noon is compared to Greenwich noon, you can work out the longitude. However, at the early days of navigation, clocks were not highly accurate, and sticking one on a boat, again, would not be conducive to getting accurate measurements. So there was various methods proposed to try and accurately work out your local time. An interesting one is called the lunar distance method. And in this case, what you're doing is you're measuring the angle between the moon and some known bright star, and also the altitude of each above the horizon. And then using tables and lots of calculation, you can actually work out what your local time is. And that will give you your distance east or west of Greenwich. Incidentally, the story of how Greenwich came to be the prime meridian is one worth finding out about, because it's full of intrigue and skullduggery and warfare and international disputes. We might have been using a Paris meridian if things had turned out differently. So the lunar distance method was one of the favoured methods of working out time for a long time.
Is that masculine, David?
Yeah, masculine was one of the...
that one.
Yeah. However, in 1707, the British fleet, returning from Gibraltar, was wrecked off the Isles of Scilly due to a navigational error, and 1,500 men died, and the Admiral Sir Cloudesley Shovel also died in the disaster, and he was to some extent responsible for it. So, after this, in 1714, the British government instituted the Board of Longitude to find a solution to the problem of navigation at sea, and they offered a prize worth what would be millions in today's currency. There were lots of interesting and sometimes extremely mad ideas, and it's again another story that's worth reading up on. And one of them was to improve the lunar distance method, another was to use the moons of Jupiter, which again are like a clock, if you like. They are very, very accurate. The moons keep going round to millisecond accuracy, you might say, but the problem of trying to measure such small angles accurately on a ship, again, was probably the downfall of this method. It was very difficult to do, and also the fact that Jupiter isn't visible for the length of the year when it's too close to the Sun or behind the Sun.
Speed of light as well.
Ah yes, the speed of light comes into it as well. That was Ole Romer who worked out the first estimates of the speed of light based on differences in the occultations of Jupiter's moons from furthest to nearest distances. So we know now that the eventual solution was the development of an accurate chronometer. Now, this was John Harrison, who was a self-taught carpenter and clockmaker from Wakefield, who spent 20 years refining his designs until he came up with chronometer H4, which was finally accepted, despite the protestations of Maskelyne, as you say.
A great story.
Yes.
Great story.
And it was taken on a voyage from London to Barbados and showed an error of only 39 seconds on that voyage. So the problem, if you like, of longitude was solved. And that set the scene for the development of proper celestial navigation, which could use the sun, the moon, stars, planets, whatever you want to, because you could now measure your longitude, measure your latitude, and find where you were. And we come to probably the quintessential tool, as we would see it today, the sextant. The first sextants were, have I written it down wrong way, 1700s. Thomas Godfrey and John Hadley developed the first sextant in the 1700s, and it turns out that when they had a look through Isaac Newton's notes after he died, they found it designed for a similar instrument, so he was also thinking about it. The original version of the sextant was, I'll give you a quick explanation of how it works first. The sextant is a doubly reflecting instrument, which means it uses two mirrors. So we have a horizon mirror which is semi-silvered, and you can see through that towards the very curvy horizon here. And it also has the index mirror, which is connected to the index arm. And by rotating the arm, you can rotate the image of the star or the sun until it touches the horizon. So by carefully adjusting it, you can get that to be exactly on the horizon. And then it's simply a question of reading the angle off on the arc at the bottom. Now, the original devices weren't sextants, they were octants. The angle here is 45. Is this a sextant or octant? I think that's a sextant, an octant, yes. 45 degrees, thought I'd put the wrong picture in, which is an eighth of a circle. But because of the double reflection, the device can actually measure twice that angle. It can measure 90 degrees. However, in attempting to improve the lunar distance method for longitude, Admiral John Campbell found that he needed to measure bigger angles than 90 degrees, so he commissioned an instrument maker by the name of John Bird in 1757 to produce a sextant where the angle is 60 degrees, or a sixth of a circle, and that can measure up to 120 degrees. So it's not a Mr. Sextant that invented it.
So you were lying. Say with confidence.
So the modern sextant is a nice light instrument. It's made of material that's adjusts for thermal expansion and moving from the tropics to the Arctic. It has things like filters on the sun side and on the horizon side to cut down glare. So it's a much more usable, much more accurate instrument. It also has a drum vernier to give you accuracies of a fraction of a degree.
How do you get that sort of accuracy if the ship's moving around?
It takes a lot of practice. The method is really just to try and get it as close as possible. And what you do is once you've got your sight, I'll demonstrate in fact. The traditional way that you see people using a sextant on movies is generally that they will go, oh, there's a star I want to sight, and they'll go like this, which doesn't work because you can never see where the star is. So what you actually do is you aim at the star, and then holding the index arm as steady as you can, you then bring the star down to the horizon. And then when the horizon matches, you can tweak a little bit, and then generally you rock the sextant, so you're rolling it back and forward to check that it exactly matches on the horizon. So it is a bit of a fiddle to learn to use. In fact, that's one of the things of celestial navigation, is learning to actually take a sight and get an accurate reading is the biggest step forward. But how does it work is the question. So celestial navigation in its most basic form, without all the hard sums, if you think that for any moment in time, remember the Earth is rotating, then for any given star there is a point on the Earth's surface which the star is directly overhead, and we'll call that the geographical position of that star. And if you're sailing along and you happen to look up and there's a star directly overhead, you think, oh, that's handy, and then you note your chronometer or your wristwatch and you get your accurate time, and you go to your celestial navigation tables, your celestial almanac. You can find for every day of the year, for every hour of that day, plus corrections that will help you interpolate between the hours. You have a set of stars, positions, sun, moon, various planets, other interesting bits of information which are all useful. So if you happen to get that star directly overhead and know at the time, you can pinpoint yourself with 100% accuracy. However, the chances of being under one of the bright stars that are listed is pretty infinitesimal. So what happens is you use your sextant to measure the angle of that star above the horizon. And based on some fairly simple trigonometry, you can then say, you know how far away you are from the geographical position. Which means that you're somewhere on a big circle round that geographical position. Sometimes a very, very big circle. And that's called a line of position, which, if you draw it on the surface of the Earth, you have a nice circular position, and you are somewhere in that very large area, which is not a lot of help, I suppose. However, if you go to your chart and you are able to mark the geographical position and draw your circle around it, you know you're somewhere on there. So the obvious thing to do is to take another site, and you take a second star and you find this is its line position, and a third one you get another line of position. And there you are. However, obviously there's a flaw in this plan somewhere. It's not as easy as that. Firstly, on a map like this, at that scale, the line you're drawing would be possibly hundreds of miles wide. And secondly, the map projection, you're turning a sphere into a planar map, and even on this, I think it's a flat carré projection, the circles would not be circles, they would be definitely non-circular by a large amount. However, on the sort of charts that are normally used for navigation, you're on a much smaller scale. And at this level of scale, the line of position is a huge circle, which is almost equivalent to a straight line. So you can just draw your lines of position on the chart at this scale, and bingo, that's where you are. That's it, without all the sums and all the fiddling about trying to take sites. Yeah.
The line of position, are you actually on the circumference of the circle, or you're just anywhere?
No, you're on that circumference.
If you're on the circumference, then you take your latitude. Doesn't that sort of narrow it down?
It narrows it down, but
Well, one of them's in the land, one's in the sea.
yeah, it does narrow it down, and that is what you would normally do, but it's never as easy as just saying, I'm on this circle somewhere and I'm at this latitude. It does involve usually about 5 or 6 separate sites to get a decent position. Or if you're doing it during the day, you can do various things, like there's a method called sun run sun, where if you're sailing on a fairly steady course at a steady speed, you can take a morning sight of the sun, you can sail, you can take an afternoon sight, and by using the 2 sights, you can then work out your position. And there's various other things using the moon and so on. It's a big subject which I'll try to compress into a very simplistic form. We check the time. Oh, we're doing not bad. However, as with all things, people don't do an awful lot of celestial navigation nowadays, I suppose. And we're all more familiar with something a bit easier to understand, which is finding your way, well, most of the time finding your way to your destination using GPS. And of course, as well as using GPS for navigating the streets, we also use it at sea extensively. And GPS is a very interesting system. It relies on a constellation of satellites, 24 of them, continually orbiting at a height of about 20,000 kilometres. And from anywhere on the planet's surface, your GPS receiver should be able to pick up at least 4, and usually a lot more, of these satellites. Now, I suppose you're thinking, well, that's not really celestial navigation, because they're not really celestial objects. But in fact, the GPS system relies on some of the most complex and interesting mathematics and astrophysics that we know of, which is Einstein's theories of relativity. Now, one of the essential things that comes out of relativity is that the speed of light is constant, unchanging, and it doesn't matter what you do, it's always 300,000 kilometres a second. So the satellites have little clocks on board, so they know their time. They also know their position in space above the Earth. So what the satellite does is it sends a little message which says, this is my position and this is what my clock reads. And your GPS receiver picks up this message and it compares its clock to the satellite's transmitted clock. And because they're orbiting at 20,000 kilometres, and if they're close to the horizon, a lot further away, it can take 1/10 of a second for that message to reach your receiver. So there's a measurable time delay. So using that, you can work out the distance to the satellite, and from that, its position relative to you. But, he said, but, there's a bit of a complication, and this is where the relativity comes in. Einstein produced relativity in two parts. The first was special relativity, which is to do with objects in motion, objects moving relative to each other. And special relativity tells us that clocks which are moving faster run a bit slower, hence the legendary twin paradox. And at the height and speed that these satellites are moving, the clock runs slower by 7 microseconds a day. After he'd come up with special relativity, Einstein moved on to general relativity, which talks about gravity and space-time. And gravity affects clocks as well, in that the less gravity a clock is subject to, the faster it runs. And as I said, they're at 20,000 kilometres up, which is a fair distance out of the Earth's gravitational field, and they run faster by 45 microseconds per day. And if you do the big complicated sum, you find that it's overall 38 microseconds a day faster. And you might think, well, I think my GPS receiver wouldn't care too much about 38 microseconds. But if you remember, the speed of light is 300,000 kilometres a second, and that actually works out an error of 11 kilometres per day. So the ground stations, which control the GPS system, monitor the clocks, and they update the clocks on the satellites to make sure that they stay accurate and take into account the relativistic variations that they're subject to. So this lets you navigate fairly accurately, or very accurately in fact. So the system in principle is exactly the same as using a sextant. If you know the position of a satellite and its distance, you can draw a big circle, or in this case a big sphere, around the satellite, and by drawing multiple spheres, your GPS receiver calculates the intersection of these spheres to give you your location. And this, with modern receivers and modern techniques, can be within a few meters, which is very handy, especially if you're trying to find your way to some lonely place away out in the countryside. So as I say, the GPS system has pretty much replaced celestial navigation, and it is in a way its own kind of celestial navigation. But unfortunately, quite a lot of navies around the world, merchant and military, have been dropping the use of celestial navigation and not teaching it to their students. However, the Americans have recently realised that in this modern high-tech world, it would be relatively likely that at some point somebody's going to hack into the system or find a way to destroy the satellites and disrupt the celestial navigation, the GPS system. So they have now returned to teaching celestial navigation. And I'm pleased to say that the British military, the Royal Navy and the Merchant Navy, both of them have never dropped celestial navigation from their courses. For some reason they teach it in the first year, which must be a nightmare for some. I suppose it gets rid of the students that don't want to proceed with it, because it's a pretty tough course. I know a young guy who's currently going through it. And they teach celestial navigation, and always have done, and hopefully always will do. And if you want to learn, you can always go on board a nice sail training ship like Bark Europa. I highly recommend the voyages. And you can be taught the basics of celestial navigation. And there's something very satisfying about taking sights, being on board a sailing ship, working out your position and feeling a connection back to centuries and centuries of navigators before you, and then checking to see if your position actually is close to the little magic numbers on the GPS receiver. So celestial navigation hopefully is not going to go away anytime soon. Okay, thank you very much. Lights on, yeah. I will also say that I do have my own sextant here. This is a real sextant. It may be made of plastic, but it is still an instrument. So if you're picking it up, try and pick it up by the frame rather than by the optics of the index arm. And you can have a look at it and experiment with it. There's a little squeezy thing to release the index arm, and the various filters and shades, and the telescope for looking through. So you can have a look at that at some point, but if anybody's got any questions, I may not be able to answer them.
Well, the sextant, you said you have to drop it down to the horizon, so you have to see the horizon.
Ah, yes.
Don't they have any sort of artificial one, like spirit level or something that can
There are.
there is when you can't actually see
There are,
really?
there are forms of sextant that do have that, and not aero sextants. Airman sextants have built-in artificial horizon because they're too high up to use the real horizon. But generally at sea, there's a big horizon.
Well, I think if you're using it on hills or something anywhere.
Ah, right, yeah. It's not really. The sextant doesn't tend to get used out in the country.
But if you're the horizon, will have no idea where that is.
You would have to get an airman sextant, which has a built-in spirit level horizon thing. But you can get those on eBay, actually. So ex-World War II bomber sextants. I'll look for those.
At the same time as the Vikings were spreading out all over Europe and North Atlantic,
Yeah.
on the other side of the world, the Polynesians were spread
yes.
right across the
Yes,
Pacific,
yeah.
from Southeast Asia right out to Easter Island and Hawaii
Oh, yeah.
and Tahiti. So how did they use the stars to know how to get from one island?
Right, yes, that's a whole other interesting talk. Because I had to kind of compress everything into the one talk, I had to leave out the Indians and similar areas of the Indian subcontinent,
Yeah.
Chinese, Japanese and Polynesians. Polynesians did use the stars, and they knew that where the South Celestial Pole was, but they tended to use other things like the waves patterns. They were very aware of that if they were sailing along, they could tell by the shape and frequency of waves which direction they were going and where things were. But they produced star maps. I don't know if you've ever seen these things. They're like bamboo, thin bamboo with like shells tied into them at junctions, and they actually have like star maps that would show the constellations. And I'm not up in Polynesian navigation, it's something I haven't looked at yet.
Because each island had associated with it a star.
That's right,
So
yes.
they knew that if you just kept sailing on that particular latitude, whichever way you went, you would reach the island.
Yeah, exactly, yes. There was, they were fascinating navigators as well, as were the Chinese and the Japanese. But not having enough time to put in everybody. I chose the Vikings because they were good for a bit of pillaging.
Not celestial navigation, but the Arctic peoples, the Greenlanders in particular, when they were voyaging in their kayaks and umiaks, they navigated, they were never out of sight of land if they could help it. They navigated by having little wooden cutouts showing the shape of the horizon when you were at a particular point, so they compared it with the hills they could see, a big stack of these little boards. No, it's not that one.
That's pretty genius.
I don't have that one.
Interesting. I'll need to look that one up, that sounds interesting. Next time around Greenland, I'll see if I can find something. Any more
I was
questions?
thinking about doing it, David. How on earth do you arrange to get onto one of these ships to do? Is it a course you do? Or
No, you just sign up. You just go online and say, I want to go. That was how I got it. The story of how I came to be a tall ship sailor is mysteriously organized. I went to Antarctica. I was going to go and see the big solar eclipse in Antarctica. My sister and I were going to go down and see that, and then we looked at the prices and we thought, we're not going to pay that. It's something like about £20,000 to go on a cruise to see the solar eclipse. So we said, we'll go to Antarctica anyway. So we went on a little cruise to Antarctica. And when I was on that, there was an Australian girl who said she'd just come round Cape Horn on a tall ship. I thought, bloody hell, I didn't know you could do that. So about 3 or 4 years later, I was looking for summer holidays and I thought, I'm going to look at tall ships. And then I went online and there's dozens of them. But Bark Europa caught my eye because it was just a fabulous picture, and they do voyages to Antarctica.
you have to pay your way then?
Oh yeah, you have to pay because you're a paying trainee, if you like.
Right. Not £20,000.
Oh no. For general little coastal voyages, the first voyage I did was from the Azores up to France, and that was, I think it was about €90 a day.
Oh, right.
All in, that's your bed, food, board and lodgings.
Weather.
Hammock.
Weather, oh,
As well.
yeah, you got free weather. But yeah, you can go sailing on tall ships. It's very easy. I would highly recommend Bark Europa because it's a Dutch boat, so quite relaxed. And the rule is, anything you may do, nothing you must do. So if you're not up to pulling on ropes, or you don't fancy climbing 100 feet up a mast, you don't have to. There's always things to do. I've been on where people have come on and said, oh, I'm just going to come for a cruise. But by about 3 days into the voyage, when everybody else is busy, they're going, I'm bored.
That's training.
Oh yeah, they have, they'll teach you all about the rope work, about the sails, how the boats evolved, how the ships evolved from their earliest times. They'll teach you how to do all kinds of knots. If you want to learn, it's anything you want to do. So generally they'll teach you, if you want to learn about wildlife, there's going to be somebody who knows all about wildlife, especially on the Antarctic trips where they take wildlife specialists. And yeah, they generally have 2 or 3 of the crew will be celestial navigators. And they'll, if you don't know the constellations, they'll teach you the constellations, teach you how to use the sextant, and then how to do all the long sums.
How many trainees shall we call it, or go on board?
Well, it depends. The Europa's a fairly small ship, so there's a permanent crew of about 12 to 14, and then maybe 50 trainees.
50?
Yeah. You're divided into 3 watches, so there'll be about 12 per watch. 12. That's about 12 per watch. Well, it can vary, 12 to 15 per watch, and you rotate around. You do 4 hours on, 8 hours off on watch. But they split it so you don't do the same watch duties. It's a fascinating experience, and I've lost count how many times I've done about 10,000, 12,000 miles on Europa now.
They last how long?
Anything from about 10 days to, if you wanted, you could stay on and do 3 or 4 months in a row.
If you don't fancy the tall ships, you can get the freighters that restock the islands in the Pacific.
Oh yes, yeah.
Go around Fiji and Tonga and everything, and that's, the ships are too big to get into the islands, so we've got little launches that take you to islands, and you can just go back and forth. And similar thing, but it's not tall ships, just general.
I don't know if you do as much training on those.
We do navigation. My friend did it.
No, right, that'll be interesting. Oh, man, look at that. Really change. Right, Tony, you got a question?
No, not a question. Could you hold, as if you were rocking about on a boat, so I can take a picture?
You've got to sway at the same time, David.
That's it, yes.
He didn't speak, obviously didn't.
Wonderful, thank you very much.
Okay.
That's okay, thank you very much.
Do we have dog watches?
Yes, we do. They're not that bad. Actually, my favourite watch is the 4 AM to 8 AM watch. It seems like madness getting up at 4 in the morning, but you get to see the sun come out, you get the constellations to start with, and because everything's cooked on board, there's always fresh bread for breakfast, so you're 8 o'clock, the smell of baking bread coming up out of the galley, you come off watch, you have a brilliant breakfast, and then you relax and lie down for a couple of hours snooze.
Then you get woken again and bowled up.
Not for another 8 hours. You get your 8 hours off, it's great.
Talking about dogs, is that one of the ways for longitude?
Oh, that was right, yes.
Winding dogs or something.
Yeah, there was a scheme that you would, somehow dogs, maybe like siblings or something, you would take one dog on a ship and you would cut a dog in Greenwich on the, at noon, and the dog on the ship would bark. Supposedly, that was actually. I did say there was a lot of mad ideas, but it was particularly mad.
Barges and rockets that went up.
That's right, yeah, and they were going to have chains of barges all the way across the Atlantic, firing rockets. Yeah, it's a fascinating story. There's a really good book by
David Sobel.
David Sobel, yes, called Longitude, which it's definitely worth a read.
It's a great book.
I've seen it.
And like I say, lots of intrigue and skullduggery going on as well.
It's actually a two-part television programme. You've seen that?
Yeah, I've seen the TV series.
Very good.
So, did you go up to the crow's nest very often?
Yeah, well, as often as I could. I love being out.
And the crew took them up.
Yeah. We don't actually have a crow's nest, or like they have a barrel on Discovery, you'll see, because in the Antarctic they tended to want to be fairly cosy. But Europe is a worldwide sailing ship, so they don't have anything up there. But yeah, the top of the mainmast is brilliant. There's various platforms. The first platform is the first top, which would normally be the artillery wing would be up there, and that's a big wide platform. It's great for sitting about, taking pictures. Up further up, there's a thing called the cross trees, which are basically just steel girders that you can stand on or sit on, and then right at the top, there's really just hang on.
You've got a climbing belt and a carabiner.
There's a two-point attachment harness that you must wear when you're climbing. But yeah, I loved it. I've got some amazing pictures of icebergs from above and things like that. I could bore you for hours. But anyway, I think it's getting towards tea time, and I've been wittering on here for quite a while.
Well, it's a fantastic story, David.
Yeah.
Thank David.